The signal arrives in the dark, thin and exact, after a tiny machine has just fallen deeper toward the sun than anything humans have ever built. Parker Solar Probe is not big, not bright, and not famous in the way rockets usually are. But the data it sent back from inside the sun's atmosphere may change how we understand the star that runs our days, powers our weather in space, and can still knock hard at life on Earth. And that is where this story opens. Stay with this channel for journeys like this, and you will keep getting the kind of space stories that turn headlines into real understanding. Picture the moment more clearly. No roaring engines now, no cheering crowd, just a spacecraft the size of a small car, wrapped behind a heat shield, racing through a place no human eye can survive. Around it, the corona glows at more than 1,000,000 degrees, a ghostly outer atmosphere that looks soft from far away and turns savage up close. On Earth, none of that looks dramatic at first. Your room is still, your phone still charges, morning still comes through the window. But the sun is never only a bright circle in the sky. It throws out storms, radiation, and a non-stop stream of charged particles called the solar wind, which is simply matter blowing off the sun and out across the solar system. For decades, scientists could see signs of that wind after it had already left home. They could measure the splash, not the source. Parker changes that. It does not watch from a safe distance. It dives in, crosses the boundary where the sun still holds direct control, and comes back carrying clues from a place that used to exist only in theory. To see why this matters, we need to step back. Most people think the sun is easy to understand at the basic level. A hot ball of gas in the middle, a bright surface we can see, and then empty space outside it. If anything strange happens, we assume it begins in the obvious part, the glowing face of the sun itself. That idea feels natural because the sun looks simple from here. It rises, it sets, it warms your skin through a car window. If you draw it as a child, you draw a circle with rays. Even adults keep some version of that picture in their heads. The sun seems like the most familiar star because it is always there, always overhead somewhere, always doing what stars do. But Parker Solar Probe was built for the parts we do not see. NASA launched it on August 12, 2018, on a Delta IV Heavy, one of the most powerful rockets ever flown. The mission was managed by NASA and operated by the Johns Hopkins Applied Physics Laboratory in Maryland. Its goal sounded almost impossible in plain English: fly into the sun's outer atmosphere, survive, and measure the place where the solar wind is born. That goal matters because the sun has been keeping a secret in open view. The visible surface, called the photosphere, is only a few thousand degrees Celsius. Yet the corona above it is far hotter, reaching more than 1,000,000 degrees. That is backwards. If you step away from a campfire, you expect cooler air, not hotter air. For more than half a century, that upside-down fact has bothered solar physicists. The mission is named after Eugene Parker, the University of Chicago physicist who, in 1958, argued that the sun must release a constant outflow of material. Today we call it the solar wind. At the time, many scientists pushed back. The idea seemed too bold. Then observations slowly caught up, and Parker's theory became part of the foundation of heliophysics, the science of the sun and its reach through space. So the little craft named for him had a hard task and a deep legacy. It could not fly straight at the sun in one clean dive. Earth is moving fast around the sun, and anything launched from Earth begins with that sideways motion. To lose enough of that speed, Parker had to steal gravity from Venus again and again. 7 flybys bent its path tighter, trimming its orbit like a stone skipping inward across a pond. That is one reason Parker feels overlooked. It did not travel like a movie rocket. Its progress was slow, patient, almost quiet. It spent years setting up the moment people would later call historic. Each loop brought it closer. Each pass tested the shield, the instruments, and the nerve of the team waiting for data to come home across millions of miles. And Parker really is a modest thing to look at. The spacecraft body is tucked behind a carbon composite heat shield only 4.5 inches thick. That shield can face temperatures around 2,600 degrees Fahrenheit, while the instruments behind it remain near room temperature. Think about that for a second. One side is hot enough to threaten steel. The other side protects delicate tools that must keep acting like careful lab equipment. Those tools had names only engineers could love: Fields, Sweep, Whisper, and Isis. But what they do is easy to say. They measure electric and magnetic fields. They count particles. They image the corona and solar wind. They watch the sun not as a pretty disk in a telescope, but as a moving system of matter, force, and shock. Parker is less like a camera and more like a swimmer putting its hands into water to feel the current. From Earth, the corona is usually hidden. You glimpse it during a total solar eclipse as pale streamers around a black sun. It looks silky and calm. Up close, it is nothing like calm. It is thin, violent plasma, which means gas so hot that atoms break apart into charged pieces. Magnetic fields twist through it. Particles race through it. Waves move through it. Structures form and tear apart faster than old pictures ever suggested. By the time Parker began its close approaches, one assumption still held strong in the public mind, and even in simplified explanations. The sun's atmosphere was often imagined as layers you could map neatly, one outside the next, like paint on a ball. Cross the boundary, and the story becomes cleaner. Stay outside, and you are just watching the spill from afar. That picture was tidy, and tidy pictures are hard to let go. Then came April 28, 2021. During its 8th close encounter, Parker crossed a crucial boundary called the Alfvén critical surface. That name sounds technical, but the idea is simple. Outside that boundary, the solar wind has enough freedom to break away and rush outward. Inside it, the sun's magnetic grip is still strong enough to pull the behavior of the plasma back into its own rules. Justin Casper and colleagues reported in Physical Review letters that Parker spent about 5 hours there. That was the moment people started saying the probe had touched the sun. NASA announced the result in December 2021. Nicola Fox, then leading NASA heliophysics work, called it humanity touching the sun. Craig DeForest of the Southwest Research Institute described the region as terra incognita, unknown land. The phrase fit. Even after decades of solar observation, this was the first direct walk into the borderland itself. Still, if you were holding on to the old picture, you could feel safe. Fine, you might say. The spacecraft crossed a known boundary we always expected to exist. It confirmed the broad map. It gave us a better number for where the edge sits. Interesting, yes. Dramatic, yes. But maybe not revolutionary. Maybe this was just the sun finally allowing us to measure what we already basically understood. And that is exactly where the story becomes dangerous in the best way. Because the closer Parker got, the less the sun behaved like a clean diagram. The border was not a smooth shell. The wind was not a simple stream. The atmosphere was not a quiet wrapper around a bright ball. The deeper Parker went, the more the neat picture remained in place, only because nobody had been close enough to break it. What we have just taken for granted turns out to be a small part of a much larger story. The edge of the sun's atmosphere was not waiting there like a painted line on a globe. It moved, bent, and fooled the eye. Write the moment your picture of the sun changed in the comments. That helps this channel build the next video around the exact ideas people are ready to rethink. Now the real reveal begins. When Parker entered the corona in 2021, scientists expected a boundary that would at least behave like a boundary. Not perfect, maybe, but understandable. What they found was something stranger. The spacecraft crossed in, then out, then in again. Instead of one simple frontier, the Alfvén critical surface was wrinkled. Justin Casper's team described spikes and valleys in the boundary. One large wrinkle seemed linked to a huge magnetic structure called a pseudostreamer, a broad feature on the visible sun. The expectation had been a smooth shell, or maybe a hopelessly ragged mess. The truth landed in between, like discovering that the wall of a house is breathing. That mattered at once. If the boundary itself rises and dips, then the place where the solar wind breaks free is not fixed. It shifts, it warps, it responds to conditions deeper in the sun. Imagine trying to understand weather on Earth if the sky itself changed height over your town from hour to hour. That is the kind of complication Parker brought home. And the surprises did not stop at the edge. Before Parker, the solar wind often seemed steady once it reached instruments near Earth. Yes, storms happened. Yes, big blasts called coronal mass ejections could crash through space. But the everyday wind looked enough like a breeze that people used calm words for it. Parker got closer and found the wind near its birthplace acting more like a river over rapids. The craft kept seeing switchbacks, sudden zigzag flips in the magnetic field. Scientists expected some of them. They found clumps of them, more common and more organized than expected. The comparison that helps most is this. Instead of a rope trailing straight behind a moving boat, the magnetic field looked like a whip snapping back on itself over and over again. Soon after that, Parker pushed the question deeper. Where did those switchbacks come from? For a while, they looked like something the solar wind might make after it had already left the sun. That would have been simple. The wind goes out, it gets messy, and the kinks appear later. But as Parker closed in, the origin shifted inward. Data tied many switchbacks to magnetic funnels rooted in the photosphere, the visible surface of the sun itself. That changed the timing of the story. The expected picture said the wind launched cleanly and became tangled later. The actual picture said some of the tangles were born at the start, near the sun's own magnetic plumbing. It was like thinking traffic only jams far down the highway, then learning the knots begin right at the on-ramp. By 2024, NASA and ESA-linked research announced another step. The fast solar wind, one of the two main flavors scientists talk about, appeared to get part of its energy from those switchbacks. That connected an odd feature to a major mystery. The expectation had been that switchbacks were side effects, noisy details in the data. What scientists found was that they may help power the flow itself, not decoration, engine work. That is a big jump to hold in your head, so bring it home for a second. When your lights flicker during a storm warning, when astronauts need shelter from radiation, when satellites struggle with charged particles, you are living with outcomes that begin in these hidden motions. Parker is not telling us a distant fairy tale. It is mapping the first pushes in a chain that can reach power grids, radio signals, and spacecraft systems all the way out here. Then Parker did something even more valuable. It stayed close longer. As later encounters piled up, the spacecraft spent more time inside the corona, where the key physics happen. Not just one daring touch, but repeated returns. The result was less like a single snapshot, and more like the start of a time-lapse. Patterns emerged. Some ideas hardened, others broke. One puzzle moved to center stage, the slow solar wind. Fast wind is one thing, slow wind is another, denser and more variable. Near Earth, the slow wind can interact with faster streams and help shape moderate space weather that still matters a great deal. Scientists had long suspected the slow wind might come in two broad types. From afar, that was a suggestion. Up close, Parker made it harder to ignore. The expectation was that the slow wind might be a single, messy category. What Parker found was evidence that two kinds really do show up close to the sun. One type, called alphvenic, carries little magnetic wiggles and switchback-like behavior. The other, called non-alphvenic, behaves more plainly. The simplest comparison is this. One feels like water with ripples running through it, and the other feels like a thicker stream without those constant little snaps. That split matters because different winds may come from different solar structures. Some scientists think the non-alphvenic slow wind may escape from helmet streamers, giant looping magnetic arches above active regions. The alphvenic slow wind may come from areas near coronal holes, darker, cooler regions where the magnetic field opens outward. Parker's images and in-place measurements did not fully close the case, but they made the suspects sharper. And then came the late 2024 pass, the one that pushed Parker to a record-setting distance of about 3.8 million miles from the solar surface on December 24, 2024. Operations teams later confirmed the spacecraft survived. A beacon tone arrived on December 26th. It had raced through the corona at roughly 430,000 miles per hour, faster than any human-made object in history. Not a dramatic movie explosion, just a tiny signal saying, "I made it through." When detailed data from that pass began to come down, scientists got something they had wanted for years: images from even deeper within the sun's atmosphere. In July 2025, NASA released close-up results from the WHISPER instrument. Researchers expected sharper versions of things they already knew. They found features that made the corona look more dynamic, more crowded, and more structured than distant views had suggested. It was like stepping from a weather map into the storm itself. Those images showed the heliospheric current sheet more clearly. That is, the giant boundary where the sun's magnetic field switches direction from northward to southward as it stretches through space. From far away, it can sound abstract. Up close, it becomes a physical place in the story of the wind. Parker also captured high-resolution views of multiple coronal mass ejections piling up and interacting. Angelos Vorlidis, the WHISPER instrument scientist at Johns Hopkins APL, said the images showed CMEs basically piling on top of one another. Scientists expected eruptions to be important. They found collisions and mergers playing out in richer detail than before. Think of waves in the ocean. From the shore, you see sets rolling in. From inside the water, you feel one wave hit another, combine, lift, and throw. That is the difference Parker brought. Why do those collisions matter? Because when solar eruptions merge, their paths can change, their fields can mix, their particles can speed up. That makes space weather harder to predict and sometimes more dangerous. The old expectation was that each eruption could often be treated as a cleaner event moving through open space. The new reality is messier. Traffic in the sun's atmosphere is traffic, not empty road. At this point, the mission had started doing something rare in science. It was not merely solving a famous mystery, it was replacing a simple mystery with a more accurate one. The corona was not just hot, it was active in ways that linked structure, wind, and storms across scales. The boundary was not just a border, it was a living, moving shape. The wind was not just launched, it was shaped, energized, and sometimes redirected before it ever had time to become the calm breeze felt farther out. There is a moment in stories like this where honesty matters more than neatness. By about 2/3 of the way through Parker's great reveal, even the scientists closest to the mission were saying they did not yet have final agreement. Adam Sabo, Parker's mission scientist at NASA Goddard, said in 2025, "We don't have a final consensus yet, but we have a whole lot of new intriguing data." That is not weakness, that is the sound of real discovery. Because some answers now seem likely, not finished. Researchers have stronger evidence about switchbacks and much better clues about slow wind origins. But the sun still resists full capture. Plasma, magnetic fields, waves, heating, and escape all interact at once. If you want a kitchen table version of that problem, it is like trying to explain steam, boiling, bubbles, and the whistle of a kettle with one sentence, while the heat is still rising. The system is alive while you study it. Yet some parts of the picture are now far firmer than before Parker. We know the corona's boundary is uneven. We know Parker crossed it repeatedly, not ceremonially. We know close-in measurements reveal the solar wind in a far less settled state than Earth-based intuition suggests. We know switchbacks are not minor oddities. We know the deepest passes can show how eruptions interact before their effects spread across the solar system. Noor Rawafi at Johns Hopkins APL put the challenge simply when talking about the solar wind's escape from the sun's gravity and magnetic control. That continuous flow, especially the slow solar wind, remains one of the major problems in heliophysics. Parker did not end that problem. It forced it into the open. It turned guesses into testable maps. It gave science a place to stand inside the question. And there is one more emotional turn here. For centuries, the sun was the thing that lit everything else. We studied planets, moons, rings, and galaxies as objects. The sun was background and source. Parker reversed that feeling. It made our own star into terrain, a place with walls, folds, currents, and weather of its own. Suddenly, the star outside your window was not a flat disk at all. It was a landscape. And here is where this stops being about one machine and begins being about us. If the reveal in this story is right, then the way we think about the sun quietly shifts from simple light source to active neighbor whose moods travel outward into our daily systems. Pass this video to one person who still thinks space weather is just a fancy name for sunlight. That share helps another mind connect the sky above them to the technology they trust every day. What changes now is not only the science paper, it is the forecast. The better we understand where the solar wind begins, how magnetic fields fold, and how eruptions stack into one another, the better we can predict what reaches Earth. That matters because modern life is strung across fragile lines: GPS timing, satellite internet, aviation routes near the poles, power grids, weather satellites, crew safety in orbit. The sun touches all of them without asking permission. Parker's data gives models something they rarely get in deep space science: ground truth close to the source. Instead of only observing the wind after it has traveled tens of millions of miles, scientists can compare distant effects with near-sun causes. That improves space weather prediction the way a storm radar improves a forecast over guessing from wet sidewalks after the rain already passed. NASA leaders have spoken about that practical side with unusual clarity. Nikki Fox said the mission lets us witness where threats to Earth begin, with our eyes and instruments, not only with models. Kelly Kurek at NASA has stressed that first-hand accounts from the solar atmosphere offer a new vantage point. That phrase matters. A new vantage point is not just more data, it is a new angle that can make old arguments fail. It also changes how we think about exploration itself. Parker is humanity's first mission to a star. That line sounds poetic, but it is also exact. We are used to hearing about Mars rovers and outer planet flybys. Those are visits to objects that sit there and wait. Visiting the sun is different. The target is an engine. It throws off particles, heat, fields, and radiation every second. To explore it, you do not land and look around. You survive a moving blast zone. That changes engineering, too. Parker's heat shield, cooling system, and autonomous guidance already count as major advances. The spacecraft had to sense when sunlight drifted where it should not and correct itself fast. At closest approach, radio contact pauses. The team cannot steer in real time. Parker must protect itself alone. In that sense, every successful pass is both a scientific act and an engineering one, like sending a probe into a furnace and asking it to think clearly while inside. Future missions will build on that confidence. Not every mission will dive so close, but Parker's work helps missions across heliophysics. Solar Orbiter, run by ESA and NASA, offers different views from farther out and at new angles. Ground-based telescopes, such as the Daniel K. Inouye Solar Telescope, provide detailed looks at the sun's surface and lower atmosphere. Put those together with Parker, and science can connect surface features, near-sun measurements, and far-out effects into one longer chain. There is also the matter of timing. The sun follows an activity cycle that rises and falls over about 11 years. Parker reached its deepest planned orbits while the sun was entering a more active period, which gave scientists a chance to watch complex behavior under stronger conditions. That is luck earned by planning. Build too early and the sun is quieter. Build too late and you miss the chance. Parker arrived as the star was becoming more expressive. As the dates become more precise, the story feels less like myth and more like a calendar unfolding. On April 28, 2021, Parker first crossed into the corona for about 5 hours. On December 24, 2024, it made its record close approach near 3.8 million miles from the surface. On December 26, 2024, the beacon tone confirmed survival. On July 16, 2025, NASA released the closest ever images from within the sun's atmosphere. Each date tightens the picture. The numbers tighten it too. Around 430,000 miles per hour at closest pass, roughly 6.1 to 6.2 million kilometers from the solar surface. A heat shield about 11.43 centimeters thick. A corona hotter than 1,000,000 degrees Fahrenheit in places, yet so thin that the spacecraft survives by managing energy, not by denying the heat exists. These are not movie numbers. They are real constraints that separate fantasy from flight. And for viewers at home, the domestic anchor is simple. The next time your map loads instantly, your flight stays en route, your satellite TV works, or your phone finds time from space-based systems, remember that these comforts depend on technology living in the sun's extended influence. Space is not far away from life. It is wrapped around life. Parker is helping us learn the behavior of the star inside that wrapper. There are still open questions. How exactly is the corona heated so far above the surface temperature? How much of the fast wind's power comes from switchbacks and magnetic waves? Where do the two kinds of slow wind begin, and how do they mix later on? How do colliding coronal mass ejections alter forecasts in ways we can model before impact? Parker has narrowed these questions, but narrowed is not the same as finished. Even so, the future is not vague. Better models will come from these passes. Better warning systems will follow better models. New papers will keep linking Parker data with observations from Solar Orbiter, Earth-orbiting observatories, and ground telescopes. Through 2026 and beyond, researchers will keep unpacking what those close sweeps recorded. The mission may be one spacecraft, but the science community around it is a growing net, catching meaning from every packet that comes down. Something else changes as well. Wonder gets more precise. We do not have to admire the sun only as a symbol anymore. We can admire its actual behavior, its folded magnetic walls, its uneven edge, its wild wind before it calms. Precision does not shrink awe. It sharpens it. The better we know the sun, the stranger and more alive it becomes. Soon, more discovery will come from the same dark gap between a dangerous pass and a returning signal. Somewhere in the next release, scientists will spot a pattern that only makes sense because Parker went where no instrument had gone before. It may be one cleaner link between the photosphere and the wind. It may be a better warning sign for storms. It may be something nobody planned to find at all. That is the true horizon now. Not merely getting closer, but understanding more each time the data arrives. We are no longer waiting for proof that the sun can be touched. That part is done. We are waiting for interpretation, for the next hidden rule to step out of the noise, for the next surprise to show that the star above us is still larger in behavior than in appearance. Save this video and come back when the next Parker results land. That way you will have a clear map in your head when the new data starts changing the picture again. So hold one image as we leave. Not the whole sun, not the whole mission. Just this. A spacecraft no bigger than a small car on December 24th, 2024, rushing at about 430,000 miles per hour through the corona, shield glowing, instruments working, radio silent, while humans far away wait for a faint tone to cross the dark 2 days later and say it is still alive. That tiny signal means more than survival. It means the wall opened a little. It means the place that lights your morning can also be studied as a real world with texture and motion and rules. And it means the future of solar discovery will not be built from guesses alone. It will be built from brave measurements, patient returns, and the quiet certainty that the next message from the sun is already on its way.